In case somebody saw the picture and wondering why it said that, that's what it is. Back to our regularly scheduled program. All right. So if this point on the image, xy1, is just this ray intersecting the image plane, that means that any point along that ray is on that, it projects to the same point in the image plane, and the points along that ray are the scaled sx, sy, and s, if you multiply by scale factor. And remember, in homogeneous coordinates, sx, sy, and s, you divide by the s to get out the new x, the new y. That's the relationship between that homogeneous transformation, dividing out by the third coordinate, and this notion that a point on an image is essentially equivalent to a ray in space coming from the center of projection and intersecting the image plane. We're going to make way more use of that in our conversation next time. We're only going to use it a little bit this time. So given that little bit of information, we can now talk about image reprojection. Here's the basic question. How do we relate two images, so I have two images, projective plane 1, projective plane 2, where the center of projection of the camera was the same? Okay, so I've got the camera and its center of projection is fixed, and I take two images. So the question is, how do I map from projective plane 1 to projective plane 2? Well, here's the answer. Basically, think of that image, or the point on the image, as we said, is it's actually a ray in space. And it's a ray from the center of projection through the image plane intersecting the image plane. And then in order to figure out how to map from projective plane 1 to projective plane 2, I basically have to figure out where that same ray intersects projective plane 2. So if I knew where that plane was, then I could just figure out where that point is. All right? And so that would be, you know, right here. Okay? So what should be clear is that in order to figure out where this ray was intersecting projective plane 2, I didn't actually have to know where in the world that ray hit. I just need to know the camera center, the location of the point in image plane 1, that defines the ray, and then I intersect the ray with projective plane 2. Where it hits in the world is irrelevant. What that means is, instead of thinking of this as a reprojection from 3D to 2D and figuring out how it projects to some other 2D plane, when I'm going from two planes that are from the same center, I really want to think of this as a 2D image transformation. A 2D, it says here, image warp from one image plane to the other. I don't have to worry about the third dimension, the 3D world. So a very cool application of this is what's referred to as image mosaics, or sometimes called image panoramas. So would you like to know how to make an image panorama, sometimes called an image mosaic, which is way easier to say than Panama? Maybe they make them in Panama. I don't know. We're going to make panoramas, and we're going to use homographies to do this. All right, so here's the basic procedure of how to make a panorama. You're going to take a sequence of images from the same position. So you might ask, well, if it's from the same position, don't I get the same picture? No, you're going to rotate the camera about its optical center. So the position stays the same, but the direction that the camera is pointing can change. Then what you're going to do is you compute a transform between the second image and the first, or the first and the second. And then what you do is you transform that second image to overlap with the first according to the correct transformation. And then what you have to do is you have to blend those two pictures together to make the mosaic. And of course, if there are more images, then you have to repeat. But wait a minute. How come I don't have to worry about the 3D world in order to put together a panorama of images that are taken of this whole big world that's got different depths, etc.? What about the 3D geometry of the scene? Why aren't we using it? Well, you can probably guess it's that thing that we said before about that when you're projecting from one image plane to the next, if they're taken from the same camera center, the 3D world is irrelevant. So I don't actually have to know the scene structure in order to paste together these pictures to make a panorama. So there's a cool way of thinking about image reprojection, sort of a natural geometry. The first is, think about, take one picture, another picture, and you'll see here that all of these pictures were taken by rotating my camera, and I've drawn it as if the camera's center of projection was perfectly aligned. Of course, it's never perfectly, but pretty close. Although you can buy little tripods that make it easy to rotate the camera right above the focal point of the lens. In fact, if some of you have a really good camera, it'll show you where the film plane or the sensor plane of the camera is, and then if you know the focal length of your camera, of your lens, sorry, let's suppose it's a 50 millimeter lens, you would measure 50 millimeters from that point, and you know that's the focal point of my lens, and you could set your tripod up so that the axis of rotation is right underneath that, and that's how you'd actually do that rotation. So anyway, so we show here that we have three images taken from three different orientations. Then what we want is we're going to project all of these images onto some single mosaic projective plane. All right? So here we're showing projecting image 1, projecting image 2, and projecting image 3. All right? And so the idea is that you're projecting everything down onto a common plane. And of course, there is some overlap, which is actually a good thing, because in order to figure this out, you're going to need overlap. But of course, you're also going to have to figure out, A, how to transform these images, and B, how to blend them. So this way of thinking of mosaics is that these are images that are reprojected on a common plane, and the mosaic is formed on that plane. Before we go further, this only works for sort of a limited field of view. But you might be thinking to yourself, wait a minute, can I take pictures all day spinning around on my tripod? Now you get to see how much hair I don't have on the back of my head. I know you've always wondered about this. Anyway, it feels like you should be able to paste together pictures going all the way around. And you can. And in fact, Photoshop and even little cameras that you buy do this for you. They're not actually projecting it onto a plane. They're projecting it onto some other surface like a cylinder. And then you unwrap the cylinder and you get a panorama. It turns out that's not actually a real picture. It's sort of it's a real picture, it's made up, but it's not a particular scene. Whereas when you do a panorama onto a plane, it's as if you had a super wide field of view camera. So it's two different kinds of things. When you do the really wide ones, it maps it onto a cylinder. So how are we going to do this? All right, so here's an example, again, courtesy of Steve Seitz. So what we're going to do is we're going to take these multiple pictures. These are from the Great Wall of China. Thank you, Steve. And, you know, what's drawn here is this idea that we've taken all of these pictures from the same center of projection. So how do we do this? Well, as we talked about before, the projection between two planes, shown here as P prime equals HP, is just a homography. Remember that from last time? A homography that allows us to map from one plane to the next. In fact, a little bit later, I'm going to show you a nice little proof that says a projective mapping between any two planes can be represented as a homography. But here we've represented it as just H, going from one set of points to another. So let's now compute this homography for the Great Wall of China. Actually, Steve did this a really long time ago, but I'm going to pretend that we're doing it right now. So in order to compute the homography, the first thing we need is we need sets of corresponding points, all right? So on the left, we have the original points, x1, y1, x2, y2, all the way up to xn, yn. We have a bunch of points. And on the right, we have the corresponding points in the second image, x1 prime, y1 prime, x2. And for now, we're going to assume that these points have been found by that tried and true method of paying somebody else to click on them. That's called Amazon Mechanical Turk, or something where, or maybe you're an undergraduate and your advisor is beating you up and so you have to do all the clicking. Or maybe you're doing this for a problem set for a computer vision class and you have to do the clicking. But basically the idea is somehow you've identified corresponding points between the two images. So what we have to do now is we have to solve for this equation, right? We know that the relationship between P and P prime is going to be this homogeneous coordinate transform, or homogeneous homography H. So how do we solve for H given some number of points? Well, there are two ways. The first way is the non-homogeneous, boo hiss, all right? Going back here, even though there are 9 variables in the matrix, we know there are only 8 degrees of freedom because it's only known up to a scale value. So we can set, for example, the last entry to 1. All right? Well, then we can set up a linear set of equations, AH equals B, where the vector now is of H where it's going to be A, B, C, D, E, F, G, H. But this H isn't the same as that H. This is the H that's all the elements of the big matrix H, and this is dumb little h. Okay, so we got A through F, pretty smart, and dumb little h. And then G's in there somewhere. You get it. There's 8 unknowns. Okay, if I knew the first 8 letters of the Greek alphabet, I would have made them that way. But basically, I've got 8 unknowns. As long as I have 4 points, I would have 8 equations. Why? Because I get an equation for the x and an equation for the y for each point, corresponding points. But I really, because my locating of the points won't be precise, I would be better if I had a whole bunch more points, and then I would do a least squares solution. And you would solve for the minimum of the magnitude of AH minus B squared, the minimum of that square, using least squares. And you've known how to do that since 8th grade, I hope. 9th grade, 12th grade, I don't know, somewhere along the way. If you don't know what I'm talking about, go learn a lot of linear algebra before we take the rest of this class. All right, but this is the non-homogeneous way. Thinking about this set of equations, we've already seen this, right? Remember when we were doing the extrinsics, and we had a whole bunch of equations, 2n of them, and we had am equals 0 because we didn't change it? So we can do just like we did before. You multiply this through, you divide out by w, and you'll get 2 homogeneous equations for each point. Right? Now instead of m, we're solving for h, and we have a whole bunch of terms, all linear in terms of h, and it equals 0. And we have 2n of those equations, where n is the number of points. And how do we solve this? We'll use that singular value decomposition just like we did last time. Or you could take that A transpose A matrix, solve for the eigenvectors, pull out the eigenvector with the smallest eigenvalue, and that was our solution. Remember, we showed that it was the same thing. That's the way for solving for the homography coefficients. And by the way, that's the cool way, because you can impress people, because you can tell them you use singular value decomposition, which has so many syllables in it, they're sure you're really smart. Once we've solved for the homography, we have to be able to apply it. So what apply it means here is I might have some point in image 1, some point at x, y, and using the homography, I can pump it through, get the x prime, y prime, w prime, divide through by w, and I get the new x prime, y prime. That tells me the location. And I have to essentially transform that first image to the second image by moving that point to that location. And I could do that for every point in the left image, and I would have transformed it to the location of the points in the right image. By the way, we sometimes refer to this transforming of the image as warping the image. In fact, we're going to talk about how you do image warps in a little bit, yeah, image warps. It's actually going to be interpolation, but that's giving away the secret. All right. So once you do that, you can take, for example, these 4 pictures of the Great Wall of China, and you can wave your magic computer vision wand, and voila, out comes what looks like a spectacular wide-angle view of the Great Wall of China. Thank you, Steve Seitz. Now, you'll notice that there are some distortions here, and one of the things I want to point out to you is that there were some distortions in the original image. Like you see here, some of the lines are bent. That's to do with distortion on some of the lenses. But in general, lines stay lines when you project them onto planes. And that's a pretty cool picture. There are other applications of essentially mosaicing pictures together. Here's one that was used for, the comment is content-based coding, which is stolen from somebody who stole it from somebody who stole it from somebody else who's now lost forever. But basically the idea here was, what we do is we have this tennis player, and you can see the tennis player is being removed. And the way that was done is you essentially take all of the pictures, and it's a camera, TV camera, that's rotating about its focal point, so you can line up the pictures. Now, of course, they line up pretty well everywhere except where the player is, and so you can use a particular method called ransack, which we'll talk about, oh, I don't know, probably 9 years from now, to figure out what the most likely relationship is between each of the pictures, line them up, and anywhere that the pixels have changed a lot, you say, oh, I'm going to throw that away, subtract that out, and that removes the player that's moving around, and what you get out is this nice big background, which is as if you had this really wide field of view, okay? And then if you wanted to have the player running around on this background, you could just play the player moving around on this different background. Lots of people have used these types of mosaics in order to be able to show you cars traveling on a really big area. So it's taken from an airplane with a narrow field of view, but it sweeps across. And it's basically building up this big background to do what's referred to as content-based manipulation, content-based coding.